I'm sure we are all familiar with this, with traditional autoscaling, where resources are being added only after traffic starts increasing, which that works. But today, we are going to be talking about proactive approach, which is using machine learning to predict the future demand and automatically scale infrastructure. And automatically scale infrastructure. Before we start, I'm going to introduce speaker for today. Um, his name is Ibukun Onyedeji. He's here. I think he's here already. Good afternoon, Ibuku. Can you hear me?
Oh, sorry.
Okay.
Hey,
Okay. So our speaker for today is Ibuku Onyedeji. He's a DevOps engineer. He has experience in cloud infrastructure, automation, CI/CD, and also Kubernetes. And he also has a strong background in fintech and industry, fintech and payments industry. Sorry, yeah. Please give him a warm welcome as he takes us through today's session. Okay. Ibuku, I think you can start. Um, start your.
all right. Good afternoon, everyone. Can please, can you hear me? Can you send a thumbs up? You can hear me, because yeah, thank you. All right. So let me quickly share my screen. All right. So if you can see my screen, can I get a thumbs up too? All right. Okay. Good afternoon, everyone. It's it's nice to be here. It's raining heavily where I am, so if you can't really hear me clearly, I apologize for that. So in this very short time frame, I will be talking about the topic predictive autoscaling, building infrastructure that thinks ahead. Um, a little bit about myself. I think Austin has mentioned most of it. Sorry, give me a second. Yes. So So sorry about that. So yeah, I was saying a little bit about myself. Hold on. I'll say a little bit about myself. Uh, my name is Lukin. Like Austin already mentioned, I'm a DevOps engineer, and I've been working in DevOps. I'm working doing DevOps for uh, different credits, fintech and payments company for the past 5 years. And as on a serious note, but on a lighter note, I like to watch football. I like to play games, and yeah, I also like to play a lot. So just a little brief about myself. So I want us to quickly follow the slides. It's going to be a short but interactive um, period as we learn about predictive auto scaling. So can someone just quickly, either in the chat or unmute and say what he or she thinks this topic is referring to, like when we say predictive auto scaling, or when we talk about auto scaling, what's the first thing that comes to your mind? Should I call names? I don't know if I should call names. All right, Emmanuel, you don't have to unmute. You can send a chat in the chat box. When I'm assuming everybody here is a DevOps engineer or is learning DevOps. Um, what do you think when you see these two words, right? Predictive auto scaling. Predictive auto scaling. What do you think is referring to in your own words? All right. Thank you. Thank you very much. Yes. I appreciate the response. So, um, although these responses are very technical, so I guess everybody is a guru on this call. But I think, but those are very correct responses. So, predictive auto scaling. If I have to explain to a non-technical person, is basically um, based on my past usage, based on my past spending, based on my past cost reports. Sorry, I'm talking about something different. Based on my past uh, usage, not past cost, based on my past usage, how do we ensure that we are not reacting? Okay, let me take for instance a time we were doing marketing campaign at the company I worked in. So marketing, they were doing a campaign. They were using a popular influencer. I don't want to mention his name, and they had to inform us in the team that hey, that we will our advert is about to go live on Instagram, and because of how huge this um, influencer is, sorry, give me a moment. Okay, so sorry about that. I'm at the office, so I have to attend to people. All right, so yeah, I mentioned that the marketers they had to inform us that their ad is going live on Instagram like 2 or 3 days before. So we had to, ensure that we have parameters, auto scaling group, and basically all checks, all the triggers are in place for um, for this kind of traffic. And it actually had an impact. When the advert went live, it really had an impact to our infrastructure. There were a lot of first time sign-ups. There were a lot of people also using the app based on that advert. So with predictive auto scaling, we go one step ahead. We go a step ahead of setting triggers, right? Setting um, baselines, setting checks to actually understanding why um, why we have this kind of traffic and when we have this kind of traffic coming into our infrastructure. So ordinarily, from relative from common sense, you say, okay, when marketing are doing campaign, when festive period. So me, I work in payment space, and when it's festive period, people tend to spend money, make transactions, and the rest. So you guys, okay, during festive period, you just have to prepare yourself for a lot of traffic and stuff like that. So with predictive auto scaling, you are going one step ahead by setting up these baselines, right, or this threshold. You're actually predicting the kind of traffic that will likely hit later. But when you now incorporate ML, I also um, added a bit of AI at the end because AI right now is the I won't say it's the next trend. I won't call it a trend, but it's like we have in every phase of I won't say our life, but in every phase of us doing our work as a DevOps, cloud, or infrastructure engineers, we have to incorporate AI, one way or the other. So apart from ML, I also took the liberty to add AI. So yeah, let's start this slide. Please, if you have any question, you don't need me to stop. You can just quickly um, signify it, drop a chat, and you I will just answer you. So with further ado, let's start the slide. So yeah, the problem, reactive scaling. I think I made mention of it just when we began. Reactive scaling. The problem is that reactive scaling is always one step behind. Um, what that means is always one step behind. So you have set this threshold, you have set this baseline. Once we're having above 50% memory, also having over 70% network throughput, uh, do either a vertical or horizontal scale. Yet we have predicted it, but it's still one step behind. How? Because this scaling is, yeah, if you're doing horizontal, you're basically adding new instances, right? If you're doing a vertical, you know, adding more resource into that same instance. Because these resources are actually physical, right? And the cloud infrastructure just abstracts that process away from you. It's still going to take time. Like for every time your infrastructure scales by maybe two or more instances, you are adding two or more virtual boxes into your infrastructure. So um, yes, it's fast, but it takes a minute or two, or less than 2 minutes, but it takes a minute for these instances to get warm up. Just like, for instance, when you're creating a VM or instance, it doesn't just start up right away. It takes a couple of seconds for it to boot up. So that's one of the problems. Code start latency. So if, for instance, you're having a lot of traffic and your auto scaling kicks in, you know, it takes this 2 minutes or less than 1 minute for it to warm up and be one with the existing infrastructure. So for a very high, for very um, network intensive um, infrastructure, that's 1 minute or 2 minutes delay can, I would say catastrophic, but it might be, might not be good enough. Let me just put it like that. So traffic spikes, excuse me. I already spoke about that when I spoke about marketing doing adverts, flash sales, viral events, uh, money ramp can overwhelm static threshold, uh, threshold based rules. So let me quickly, sorry about that. Okay, sorry, my laptop just quickly. So let me quickly talk about that traffic spike. So, um, for instance, now you have done a reactive scaling, which I spoke about in the first slide, where you, excuse me, you set a rule. Okay, if CPU goes beyond 70 percent, add 2 instances and stuff like that. The system watches that metric, right? Then when the metrics hits, right, or when it crosses that line, that's when it kicks in. So at that moment where you're having that, where that metric has crossed that line, or where you're having that traffic spike, your user are already experiencing slower response time. So excuse me, you have a VM. Let's just say you have a single VM of 8 vCPU, 12, no, 8 vCPU, 64 gig RAM, and you have an auto scaling policy, right? And you just, okay, when 70% of the CPU is being used, let the auto scale kick in. At the time it reached that 70% auto scale, your users are already experiencing some form of latency, some form of lag. So one way or the other, your users are already impacted. And coupled with the fact that you mentioned that it takes 30 to 90 minutes for these instances or these resources to get warmed up and establish, database connections, dependency connections, and using Redis, using RabbitMQ in your infrastructure, and all that dependencies for it to get warmed up, right? It doesn't just the auto scale doesn't just kick in and start working out of the box. It takes a couple of seconds or minutes, right, for it to warm up. So when you have that traffic spike, you are actually reactively um, scaling. So um, that leads me to my last point on this slide, over provisioning. So because of fear of this, right, because of fear of what I just made mention of, um, users experiencing latency lags, and for these resources to get warmed up in terms of like database connections, dependency connections, pulling the container image. If you're running a container-based infrastructure, ECS or EKS, or any Kubernetes product from any cloud platform, uh, it takes a couple of minutes for it to get warmed up and do everything. So, due to the fear of that, a lot of companies that know and have encountered over provision their infrastructure. So, take for instance, right now I have a business that I do not need more than 2 VMs or 2 instances at let's say 2 vCPU, 80 gram on both instances, and because of fear of what if one day marketing does ads, or what if this is a festive period and I get a lot of customers, I get a lot of people using my application and stuff like that, hitting my website. I don't want any form of lag. I want everything to be going smoothly. How do I combat this? I basically it will step out. All right, so over provisioning. So let me just go back. Let's take for instance, I'm a small company. I don't need more than for those of us familiar with AWS, I don't need more than two T2 micro server. I think T2 micro is the smallest server instance on AWS. That's I think one vCPU, 2 gig of RAM. I don't need more than two servers. But because I'm like, what if one day my TikTok post gets viral, something of um, I don't know, I'm doing sales, I'm expecting customers. Instead of having a T2 micro, I'll do a T2 medium. And basically, that's like a buffer for me because it's already running. It can swallow or it can accept any form of traffic I'm going to get. But you know, in my experience, more often than not, the business doesn't get to use that capacity. So it's always at least 40% wastage, paying for what you're not using. And every month, the cloud service provider will always come and collect their money. So, and it's also a bad practice over provisioning. So, these are few of the problems with reactive scaling. Is what is kind of normal. What we, as a demo engineer, it's one of the first things or one of the first few things you learn in terms of like um, availability. So, uh, quickly to the next slide so that I don't, interrupt anymore. Okay, so reactive versus predictive. So with reactive, I'm just going to go through this slide. Um, Respond after threshold breach. Um, While the machine learning is scales before demand arrives, 2 to 5 minute lag to fully scale. 15 to 60 minute forecast horizon. Um, so let me just quickly explain that. So for instance, in that um, 15 to 60 minute forecast horizon, it means that once your machine, uh, once your ML, right, learns your pattern, right, once it like feeds off the patterns in your infrastructure, it demands 15 to 60 minutes into the future. So for reactive, it takes 2 to 5 minutes to scale, right? Because I mentioned it has to warm up, but for ML, what's going on? sincerely apologize. Like, I went to my office. I can't really stop anybody. All right, so I'll just quickly run through the slide so we don't get any more interruption. So yeah, you have fed your ML model um, patterns, right? And if your ML model says in 20 minutes you need 12 instances instead of your 8 that is currently running, you can start spinning those 4 extra instances before the traffic arrives. So those instances, by the time the traffic hits, those instances are already warm. They already made their database connections, dependency connections, booted up and everything. So for reactive, that baseline, that threshold has to be crossed. That line has to be crossed before the scaling kicks in. But based on, based on data set and everything that you are fed into your model, it's have this 50 to 60 minutes forecast horizon. So, I mean, the word horizon, like you're looking into space, you're looking far ahead of you. So it has that 15 to 16 minutes focus horizon. So that line means. In reactive, over provisions as a safety net. So most people, because of these first two issues, right? On these first two issues, they just tend to over provision, so they don't have to deal with these two, which is bad practice, and it leads to waste. Excuse me. But in uh, predictive, you can basically right size from the get go based on what you get from your models. Then reactive, basically CPU slash memory metrics only. But with machine learning, because of the context you have fed the model with, it can have multiple signals, right? So traffic, events, business, it's more holistic than your normal reactive scaling. Then the last one for reactive scaling is no learning, no adaptation. Why for ML? It continually learns from patterns. So, for instance, what if what was obtainable today is not obtainable tomorrow, a model basically a well-written model, a well architected model will basically want to learn from uh, data. Why are we scaling now when we didn't scale before for this same event, uh, for this same event or trigger? So please again, I will have to apologize for the breaking transmissions multiple times. If you have a question, you can send it to me in the chat. I will answer. All right. So how it works. So the we came here to quickly do a bit of understanding how machine learning powered predictive autoscaling works, right? And I will quickly brush into it because I can see a bit of the essence. Um, collect metrics, feature engineering, ML forecasting, scaling decision, feedback loop. So I'm just going to take it one after the other. All right. So first one, uh, collect metrics. Collect metrics here, can be also classified as data collection. So most autoscalers, right, they watch one or two metrics, which is CPU and memory. But these are like lagging indicators. So by the time the CPU has already spiked, by the time the CPU spike, the traffic has already arrived, it's already spiked. So the users are already feeling that throttle on their end. So with ML models, um, more richer input, more context, right, is needed to make it accurate forecast. So you're just not looking at all CPU and memory spike. You're looking at a holistic kind of prediction into your infrastructure. So, for instance, um, you want to collect more than just CPU and memory, right? You want to collect um, application metrics. What are metrics? Application metrics are things like your request rate, your latency, right? Or latency percentile, your error rate. For instance, the request rate is a very important indicator. In fact, what is the leading indicator of why your CPU rises? Because just from what the name implies, it shows the rate of the application being requested or being called by the client or by the end user. So, of course, the request rate is high. Your CPU will actually feel it. So, if you have more context of your request rate, you already know what is going on with your CPU. Or like, you just say, oh, my CPU has spiked or my CPU is high. So let me not overflog collecting metrics. I think is straightforward. The second one is feature engineering. What is feature engineering? So take for instance, raw logs, right? Raw logs or raw metrics, they are noisy. So if any of us worked on AWS or GCP or any cloud platform, if you go to your instance metrics, you see that on the different graphs showing different metrics, you can probably see the graph going in and out, in and out. Excuse me. This is very noisy because these are like momentary spikes. It may not be coming from a client or the user using your application. It may just be, the network over there at data center, or just, an internal process in your kernel running or doing stuff. So if you feed this kind of metric, these raw metrics into your model, it it tends to struggle because that data is full of, like I said, momentary spikes and a lot of noise because you're not imagine my if I'm running an Ubuntu server now, imagine my kernel is doing some kind of update and on the dashboard I'm seeing that kind of spike. It, I can start, to investigate what is not even important or what's not even there. But you want your MM model to basically transform raw data or raw metrics into meaningful signals, right? That the model can also learn from, and you can also understand and make sure that it is very clean. So, in feature engineering, the most important um, feature or feature type is the lag feature. So, what's the lag feature? A lag feature basically answers um, the lag feature basically answers what was traffic like yesterday. Like what was traffic like at this point in time yesterday? What was traffic like 4 p.m. on 25th of June? So you're asking this question tomorrow, like, okay, let me use 24th. What was traffic like 4 p.m. on 24th of June? Was it stable? Was it steady? Was it shaky? You understand? Does the traffic look the same as what we have right now? Is there any difference? Is there any plus? Is there any positive or negative difference? You know, then with that, you have basically, you know, smoothing out the kind of data you want to feed the model. You're not just going from CPU spikes or memory spikes. For instance, now if I'm running, I'm using for instance, I'm using Argo CD for GitOps, and I just run a CI/CD pipeline, and my Argo is basically picking up the changes and updating my pod or updating my cluster, right? Or doing a rollout restart. The memory will spike. It may not be as high as a client using my app, but my memory spike. It has gone from, and if I'm just taking that as my source of truth, I will just go and log that as an issue when it's not an issue. But I'm going from that into understanding what is going on with my infrastructure, go on with my application. Is the traffic at this time yesterday, is it the same with what we're getting today? If it's the same we're getting today, is it the same as is it the same on Tuesday or Monday? And if it's not the same, is it higher? Is it lower? When you clean up this data and feed into your ML model, right? It gets to understand, also learn, right, from the information or the data point that you give it. So I'm trying to be fast, but I'm trying not to brush over things. So the next one is ML forecasting. So for ML forecasting, um, okay, this is this topic is very interesting and very big topic. I'm just trying to quickly brush over everything in good time. So ML forecasting. So basically the step here is you give it your historical data, right? I just mentioned if my traffic is the same today and yesterday. So you give this kind of data, and there are tools, right? For instance, I know there's a tool by Meta, I can't remember the name, that basically does this ML selection and forecasting. If you just search it, ML model forecasting tool by Meta. Can't remember the name. So what it does, it's you feed it historical data, right, and it automatically detects weekly. It automatically detects weekly, daily, and also seasonality, right? Because I mentioned festive period, holiday period, so it's not just weekly, daily, or monthly. It picks all those things, and you train it on those data. So, for instance, I do my research for the past 1 year, and I take things down. On the 1st of January, we have this kind of traffic. On the during Eid al-Kabir, that's Big Salah, we have kind of traffic. During Christmas, we have kind of traffic. On the mid-year, June 1st to 10th, traffic reduces. I, basically clean this data, right, and feed it into that tool. I know it's by Meta, I can't remember the name. And they have other tools, right? It basically gives me that kind of trajectory, right? What to expect, what not to expect, to a very large, to a very close margin. So I don't, it not is 100%, right? So, but if I can clean that data point to a very large extent, give it historical data, give it more context, which falls in this step two, right, into a model, I can get forecast into the future, right? Um, I get information or data for me to work with. So you can also train it, right? You can also train it to understand past patterns and also, develop new patterns, right? So for instance, I I did sales around August last year, but I'm going to do sales in August this year. I want to do sales in November this year. So how so like that the data has changed. You understand? So you have to train it to put that kind of change in mind. If, for instance, I'm working in a company, we just and the attention has changed from a product to another product. So that product will not have much users again. You have to also put that into your model for it to adequately forecast it correctly for you. Scaling decision. So with the forecast, you can basically make your scaling decision, and you know that you are 90%, at least 90%, if you are doing it correctly, correct or prepared for any anything that may likely happen. So you use your forecast, right, in number 3 to make a scaling decision. And number 5, feedback loop. I think this is very This is very common in the DevOps space. You always iterate, you always have to, take feedback and improve, optimize your model, optimize your pipeline and stuff like that. So feedback for the users, for the business. So you as a DevOps engineer, you're taking feedback based on what your model is telling you. And also the model itself is taking feedback from what is happening, in right now, like currently. So yeah, that's about that slide. Go to the slide. All right. So I'm just going to quickly brush through this slide. So step 1 is so these are just basically steps in setting up a MM model. So setting up a multi-signal data collection, you feed the model the right inputs. These are the metrics, infrastructure metrics, application metrics, business signals, external context, white matters. CPU alone misses demand surges until they are hitting you. Request rate is a leading indicator why CPU is lagging. Business context. So for instance, like I said, if you're running advert, you're running promo, these are not what is already, this kind of context is missing from traditional auto scaling. So with machine learning, you can basically provide, or with ML, you can basically provide this context. Step 2, feature engineering dimension. You can give it different feature key types. So transforming raw metrics into predictive signals, traffic. So these are lag features, traffic at what period of day. So T1 hour, T-1 hour, T-24 hours, T-7 days, what traffic like 1 hour ago, 24 hours ago, 7 days ago. Rolling averages. What's the average traffic? What's the average latency in 5 minutes, in 15 minutes, in 1 hour windows? You can do more than that. Seasonality encoders, hour of the day, days of the week, or month, event flags, holidays, promo, deploy incident, and stuff like that. Rate of change, how fast is traffic accelerating? So, for instance, I'm running an e-commerce app, and today I'm doing 1,000 orders. Next week I'm doing 2,000 orders. So it's a key feature that I need to feed into my model. So rate of change, how fast the traffic is accelerating. Step 3, I spoke about this. Okay, I think Prophet is the one that by Meta. These are some ML models for demand forecasting. I think Prophet is the one by Meta. I'm not really sure, but these are some models that you can use to for traffic patterns. So you feed these kind of informations right into these models. Yeah, they have their use case. So yeah, training and validating the ML model. So this beauty from historical data to production ready forecast. This is, give 4 to 8 weeks of time series metrics. Basically, I've mentioned that kind of data you want your model to look at. Feature pipeline, I also explained that earlier. You train it, you validate it, you evaluate your accuracy, then you deploy the model. I can't really go into details because of time. I'm pressed for time. So you can start simple with Prophet. I think Prophet is the one by Meta. You can start playing with this on your own. So step 4 is from forecast to scaling action. So why is it working? Why is demand in 5 minutes? Do you scale up? Do you hold steady? Do you need to vertical scale or horizontally scale? And stuff like that. You make your scaling decisions from your forecast. And the feedback loop, monitor, you measure, you detect the accuracy, if it's accurate, if not accurate, you retrain based on what you have measured against, and you also like promote. So if you're putting new data and train it, the model, you have to promote that new changes into your deployment or into your infrastructure. So um, your improvement is not meant to stay under the table. It's meant for infrastructure to feed on. Okay, so the timeline of what happens before traffic arises. So you can see it comes here, T minus 30 minutes, the ML model forecasts traffic spike. T 20 minutes, traffic decision engine triggers scale up. T minus 10 minutes, new instances warm and healthy. T minus 0 minutes, the actual traffic, the actual spikes arrives, but the capacity is ready. Like there's no lag, there's no problem, there's no anything, there's no warm up or boot time. It's already prepared, waiting for the traffic to get to your infrastructure. And T plus 30 minutes, that is after the whole traffic and spike, it gracefully shuts down or closes. It gracefully scales down or shuts down, whatever you want to say. Uh, Plugin. So if you are running Kubernetes infrastructure, this focus will help. These tools will be helpful to you for you. Kubernetes horizontal Autoscale, Customer API by Prometheus, and ML prediction service and the likes. Really sorry if I'm rushing through, but I have a meeting very soon. Supercharging ML with AI. So basically, the same way you look at ML helping you to uh, predict your auto scaling, to predict your scaling, you just do that with AI. Right? You do that with an AI model. You know, you, they, I think you can use Olama. Olama is open source. You can use Olama, or you can use any. If you have the money, or your company has the money, you can use OpenAI or Anthropic, that's Claude, to just basically intelligently understand the infrastructure, which will help you forecast better. All right. So reward impact 40% in scaling, less scaling latency, lower cost compute, you maintain SLAs and faster responses to surges. So this is getting started. So if you have a project like this, it takes within 9 to 12 weeks to go through some observing to deploy. The key takeaways for this short session is that ML models are the backbone or the tools you use to learn traffic patterns. Feature engineering is where most of the predictive power comes from. You have to have good features. You have to have clean data points for your model to work effectively. You have to integrate this into as custom metrics, not to replace the backbone of some of our infrastructure like Kubernetes, ECS, and the likes. And AI basically enhances ML. Sorry, I couldn't talk much about it because of time, but with AI models integrated on top of ML, right? You get that intelligence layer on it. Um, yeah, thank you. Any questions, please?
All right, thank you so much, Ibuku, for that wonderful presentation. Before we move to our next section, we'll be taking our question and answers after the second speaker has taken his section, all right? So I'd like to take a few minutes to introduce the organization behind this event and share a bit of what we do, our missions, our impact, and everything about the organization. Please direct your attention to the screen as I'll be sharing the slide now. All right, so this is Beacom Dev Center, and then here we help tech talent to grow. We develop tech talent, so we run our Beacom Academy, our Beacom internship program, our Beacom apprenticeship program, and also the global tech program. Then we enhance tech talent. We'll do the Beacom Tech Network, the Emigrate Tech Visa, the Beacom Mentoring Platform, and Beacom Tech Career Coaching. And also, we do startups, which is the Labs by Beacom. So with all these, we help our techies to grow and make them globally attractive in the tech industry. So Beacom Dev Center is a multi-location technology talent development and solution platform. So at the academy, we utilize the Montessori approach in training participants in basic skills needed for modern technology and ecosystem. And then in our internship, it is designed to enable people intermediate skills level gain mastery and expertise over a period of time. Then the apprenticeship program enables industrial attachment at various skills level to gain experience on the job training. Then we have the light space also, which we have here in Lagos and every other places in Nigeria. So I'll be dropping those links on the chat box so you could take your time and go through this in case you'll be interested or you have to share with someone who would be interested in that. Also, I would like to drop the feedback review section also on the chat box. Please ensure that you fill the feedback form as this will help us to improve on our future events. Thank you very much. All right, the second speaker can now.
Okay, thank you. So just before I go, I saw the question in the chat by Michael, which is a very good question. He asks, what happened with days where there are anomalies, where the predictive auto scaling doesn't catch? Yeah, yeah, but I'm running out. For example, in the case where a brand tied to application randomly goes viral online and pulls in a lot of traffic. So, yeah, to answer that question honestly, right? Predictive autoscaling is excellent because it forecasts known patterns, right? Like you rightly said, what happened when there are anomalies. So, as much as we want to predict almost everything, we can't really see the future, right? So, like your question said, is randomly what happens when a brand randomly goes viral. So, in my presentation, I made mention of it forecasting known patterns like daily cycles, weekly trend, seasonal trend, scheduled events, but a random viral moment by definition is outside the kind of training distribution that it will entail. So because the model has not seen it before, it won't predict it. Because for instance, I told you that if you are doing it, we're feeding the ML model historical data of the past 1 year. I have not been viral in the past 1 year. It won't be able to um, it will be able to get that. So that's why I say nothing is 100%, but to a larger extent, it will um, it will save you from a lot of headaches. Yeah, but the other things you can do to mitigate um, this scenario, you can. That's why I made mention of adding AI on top of the ML. So um, if you add AI on top of your ML model, what you get is so let me just quickly. Okay, so you add AI on top of the ML, you're adding an intelligence layer on top of your ML to kind of So just the way you are texting or you're using a chatbot, right? You are basically giving it patterns or giving it signals that the ML that ML model was not designed to watch. So with your AI, on top of your ML, you can say, okay, my Instagram might pop one random day. My social trends might influence the kind of traffic I'm collecting. Because these AIs are large language models and they are real-time reasoning system, right? Because your AI today, they don't have knowledge gap like when it started. Sorry, time gap. Like when OpenAI started with ChatGPT, you say that they don't have real-time knowledge, but now they have improved greatly. So if you add an AI layer to your ML model, it will basically help you in you know bridging that gap I cannot really predict with your model. So I don't know. I hope I'm able to answer that question. All right. Thank you.
Thank you, Ibuku, for this wonderful presentation. Um, so I will be going on to the next presentation. I'll be sharing my screen. Okay. Confirm if you can hear me or see me.
Yeah, I can hear you, but I can see you.
What about now? Can you see me now?
Nah, no. Or maybe I don't know. Maybe it's from my end. Can anyone else see you?
Can anyone else see me?
No, I can see you. I can hear you.
Oh, let me try joining.
Okay, what about now?
Yeah, I can't see you. I mean, I could only see you for like a few seconds, but at that point I couldn't hear you. But so now I can hear you, but I can't see you.
I think it's going to connect. It's currently raining here, and the network is just bad. Okay, let me just continue. Jeez. Okay. Okay. Please confirm if you can see my slide.
Yes, I can see your slide.
Okay. So I'll be talking about um, predictive auto scaling. I'm sure we are all aware of the topic. Um, so okay, this is what we are going to cover today. We are going to covering the problem with reactive infrastructure, how traditional auto scaling works and breaks, and what predictive auto scaling actually is, and the machine learning engine and data pipeline behind it. Then the number five, we are going to have the real world architecture and examples. And the last one, trade-offs and when to actually use it. Okay, let's start with the problem. And this is the problem we have here. Reactive infrastructure is always behind. You understand? So here is what typical sequence looks like when a CPU, when a traffic spike hits. So we have the at t plus 0, the spike begins. At t plus 2 minutes, CPU finally crosses the threshold and the alarm fires up. We have the at t plus 2.5. Um, the auto scaling groups get the signal. At t plus 6 minutes, the new instances are finished rebooting and also passed the health check. So and they are actually serving the traffic. So we got roughly around 4 to 6 minutes window where your system is under provisioned and the users are already feeling it. You understand? Slow responses, um, timeouts, errors, this whole thing they are feeling it already. And here is the thing: for a lot of workloads, the spike was actually very predictable. So you knew Monday morning was going to be busy. You knew the flash sale was going to be live at noon. So you knew the match started at 8 p.m. So the system wasn't just looking ahead. Um, so for predictable traffic, Monday spike, scheduled events, flash sale, this lag is entirely avoidable. You understand? So this spark, we saw it coming. The system wasn't just looking ahead. We saw it. So the next one is how traditional auto scaling works. So if you look at the slide here, so you can see it is a sample feedback loop. If you look it here, you have the metric, the threshold, the alarm, the action. Um, let's just say CloudWatch. Yeah, CloudWatch is watching your CPU. It crosses 70% for 2 minutes. Then the alarm fires up. So auto scaling groups get the signal. The new instances spin up. Then that in the ELB, which is the less elastic load balancing registers, then I'm done. That is, everything is done. So for gradual and sustained load increases, this works, this works perfectly fine. Understand? Unpredictable is one of the, if you look at it here, the unpredictable one of traffic box. It is one is also fine eventually, but where it breaks down is exactly where a lot of real world workloads live. So sudden spikes, see it here, sudden spikes, short bursts where the instances come up after the spike is already gone, and the predictable recurring patterns where you're constantly reacting to something you already know was coming. So the issue is that the system is looking in the rear mirror, and it only knows what has happened. You understand? So the next slide is what predictive auto scaling actually is. So predictive auto scaling uses historical data. So instead of responding to what is happening now, you use historical data and machine learning models to forecast what is about to happen and pre-provision resources before the demand arrives. So if you look at the two code blocks at this side, you can see it here. If you look at the code blocks there, reactive scaling says if current metric is above threshold, scale. You understand? And predictive says if my forecast for X minutes from now is above threshold, scale now. So that is the whole shift. You are not just waiting for the metric to breach, you are reacting to what model says is coming. So the simple analogy is reactive is turning the AC on when you are already sweating, and predictive is checking the weather forecast and cooling the room temperature um before your guests arrive. So that is it. So the next slide, we have the machine learning engine behind it. So this is this is I'm going to say what is the predictions. Can be it is a time series forecasting model, and there are a few common choices depending on your use case. We have the LSTM, yeah, which is the long story short memory. This is a deep learning approach. It is very good at capturing long range dependencies, seasonal trends, weekly cycles, higher compute cost, but very capable on complex patterns. And number two, we have the prophets. Um, the prophets, sorry, the prophets, which was built by Meta, um, is purpose built for business time series data. It handles seasonality, holidays, and missing data, and the missing data really way out of the box. So if you're just getting started, this is usually where people usually get started, and this is where I would point people. We have the number three, which is the ARIMA. Um, this is the classical statics approach. You understand? It is a lower compute overhead. It works well for stable and regular patterns. So what the model trains on is historical request rate. You understand? Historical request rate. Um, CPU memory over weeks or months, time signals, and hours of the day, um, days of the week, known events like deployments and marketing campaigns, and for some companies, external signals like sports fixtures, yeah, or social media activity. And the critical output is not a single predicted number. It is a confidence interval. Understand? The scaling decision is driven by the upper bound of that interval. So the system prepares for the realistic worst case, not just the average. Okay. Um, the next one we have the data pipeline, metrics to scaling decisions. So let's look at how this actually flows from raw metrics to a scaling decision. Stage one, we have matrix correction, CloudWatch, Prometheus, Datadog, where your metrics live. See it here. Um, this is where your metrics live. Then we have the stage two, which is the featuring engineering. You understand the featuring engineering. This is normalizing values and creating lag features, rolling averages, encoding time signals. So this is where raw numbers become inputs. So the model can actually learn from it. Um, the stage three, we have the model with inference. This is forecasting models. It runs on schedule. Let's say every 5 minutes, and outputs predicted load plus the confidence interval for the next 30 to 60 minutes. We have the stage four, which is scaling decision engine. Um, compares to the focus scaling. I mean scaling decision engine, which is the stage four. It compares the forecast to your capacity thresholds, and it calculates the required instance counts. We have the stage five, which is the actual scaling action. Your ASG, which is auto scaling group, HIPAA, CADA, all these provisions, let's say, or CADA, the provisions resources X minutes ahead of the predicted peak. And there is a critical constraint. If your instances take 4 minutes to be ready, um, your prediction window needs to look at least 4 to 5 minutes ahead. You understand? The lead time has to be exceeded the spin up time, or you haven't actually solved the lag problem. You understand? So we are going to go due to time. So it is almost time, and this is AWS predictive scaling, which is the native. Okay. Now, if you are running on AWS, you understand? So you don't necessarily need to build any of this yourself. You understand? So the predictive scaling is built directly into EC2 auto scaling groups, which is the ASG. So AWS trains 14 on the last 14 days of your CloudWatch metrics. You understand? It identifies daily and weekly patterns, and the forecast load up to 48 hours ahead. And it also creates scheduled scaling actions automatically based on the forecast. You don't need to write any single line of machine learning code. It handles everything. And the Terraform config, I'll look at it. On the right, it shows what enabling it looks like. The key parameter, the key parameter is scheduling buffer time. set to, you can see set to 300 here, which means AWS will scale out 5 minutes before the predicted peak. Then that is your lead time buffer. It also supports the, and see it here, it supports the CPU, network application load balancer request count, and the custom CloudWatch metrics. For a lot of use cases, this is all you need. You understand? And the next slide, we have the custom machine learning. When native isn't enough, when to go beyond AWS native. So there are cases where AWS native won't just cut it. You understand? The main ones are your traffic. Your traffic signals, they come from outside AWS. You understand? So the social media activity, even the third party APIs, internal event calendars, all of them come outside. So the number two, we have the, can see it running on Kubernetes. You're on Kubernetes and need horizontal pod autoscaler, or Kubernetes event driven autoscaling integration. So this, the number three, we have unique signal inputs, combining request rates, predicts, and database connection count together. They all count together, and your traffic has irregular pattern that a 14-day window doesn't capture well. So the custom stack I would typically reach for looks like is Prometheus for metrics, a Python pipeline using Prophet or LOSTM, and prediction API built in fast API running on schedule. Header scaled object as the trigger, and Kubernetes HPA, adjusting replica counts. So the honest framing for when to go custom is when the cost of misprovisioning, either over provisioning as a safety buffer or under provisioning causing, which is causing the user impact, exceeds the engineering cost of building and maintaining the pipeline. That is your break even point. So the next slide, um, we have e-commerce flash sale. So the scenario. So um let's look at the real example. Let's look at example here. Online retailer, which is flash sale announced 24 hours ahead. With reactive scaling, the first surge cost about 4 to 6 minutes of degraded checkout every single time they ran one of these events. So before the predictive spike hits at T plus 0, then the alarm fires at T plus 2. So instance is ready at T plus 6, which is 6 minutes of elevated errors and abandoned cart. So after predictive scaling, the model was trained on 6 previous flash sale events. So it is forecasted the spike window at 12 12 o'clock to 12:45 p.m. So the system previsioned at 11:52. By the time the spike arrived, full capacity was already online. You understand? So the results table tells the story, which is P99 response time at peak went from 4,200 milliseconds down to 380. So error rates went from 8.3% to 0.2%. You understand? So over provisioning post spike dropped from 40% to 8%. And the estimated revenue protected by not having that outage window was around $180,000. So let's say 10 minutes of head start. That is all it all took. Understand? So the next slide, I think the time is already catching up. Miguel streaming match night. Um, the second example we are going to see is sports streaming platform. Let's just say major match every week, and every week the exact same traffic pattern. The model learns its code. Please confirm if you can still hear me. I don't know if I'm still audible.
Yeah, I can.
Can anyone? Okay, thank you. So let's the sports streaming platform, which is a major match every week. Understand? And it's uh, sorry. Okay. So the streaming platform, they have a major match every week, and every week the exact traffic pattern, which the model learns its code. Understand? It learns the code and how everything works. So traffic starts building at 15 minutes before the kickoff. Understand? So it peaks right at kickoff plus 2 minutes, sustains for 45 minutes, um sharp drop at halftime. I'm going to go fast. My system is about to go off. Um, Sharp drop at halftime, second spike before the second halftime, which is a full time drop. So the Prophet model was trained on 3 seasons of match day traffic. So the fixture calendar was ingested as a feature, yes, including the match importance and the expected viewership. So the system pre-warns transcoding workers and CDN edge capacities, which is 20 minutes before kickoff. It scales down aggressively at halftime and backs up before the second half starts. Let's see the results. Zero buffering event at kickoff. You understand? CDN cost reduced by 22% of compared to always on provisioning, and the engineering team stop getting paged on every match night. So you can see now. So the cost, we are going to go back to the next one, which is the cost, the scaling smarter, not just faster. So let's look at it. Um, okay, you can see always on buffer. Predictive scaling isn't just performance story. It's also a cost story. You can see the always on buffer here, 214 instance hours a day. Reactive scaling, 160 instance hours per day. Predictive scaling, 120 instances hours per day. So this is 33% lower monthly cost versus receive, 50% monthly cost versus always on. Okay, the next slide we have the trade-offs. Honest, which is honest. Um, so to be honest, about where this breaks down, we have four main trade-offs. We have number one, which is the model drift. So your traffic pattern changes. A new product is launched, different user behavior, seasonal shifts, model trained on old data. Um, we start making bad predictions. So you need to reschedule your and retrain baked into the pipeline. You understand? The code starts. So if you are launching something new or don't have data yet, the historical data yet, there is nothing to train on. You need to have at least 2 to 4 weeks of metrics before the prediction are available. So reactive scaling is your only option until then you have here, which is the prediction errors. So the model will sometimes be wrong, it will not always be right. So this is not just, it's not optional. It's not optional. You must run reactive scaling in parallel as a safety net. So predictive handles the forecasting patterns, the reacting catches the unexpected. They are not alternatives. So next one we have the operational complexity, which is a custom machine learning pipeline is is a real ongoing commitment. A model to retrain, monitor for drift, debug when predictions go sideways, and that is the engineering we need to count for. Understand? So, and the last thing, which is don't turn off reactive scaling once predictive is working. So I've seen people do this. We don't need to do this. So we need to use both. Understand? So the next one, they have predictive versus reactive. When to use what? You understand? When to use predictive and when to use reactive. So when should you use predictive and when should we use reactive scaling? So use predictive when you have clear repeating traffic patterns. So you have at least 2 to 4 weeks historical metrics to scale up the lag is causing. You understand? So over provisioning costs are very significant, and the team, maybe your team has 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 capacity to maintain the pipeline. So with stick with reactive auto scaling when traffic is highly unpredictable and pattern is free, and you are in early stages where with limited data. So the workload is low traffic, cost insensitive, your container spin up in under 60 seconds, or you already stretched thin on engineering bandwidth. Understand? So the best practice is to run both. Yeah, run both, because predictive handles the forecasting load, reactive catches the unexpected. So they are not just layers. Understand? They are layers, not alternatives. So three things to remember. Three things to remember. One is reactive auto scaling is always late for predictable traffic patterns. The lag is entirely unavoidable. So you already know the spike is coming up. The number two, we have the predictive uses machine learning to forecast demand and pre-provision before the spike. Understand? So better performance, lower cost at the same time. So the number three, we have the is not just replacement for reactive, it is a layer on top, which is run both. Thank you for listening. I'll be happy to take any questions. And this comes the end of my um, presentation. Um, any question? I think we're almost done. We have 10 minutes to close up, which is a 5 o'clock. I'll be happy to take any. Okay, I will take that as no question. Hello, Gloria. Can you hear me?
Yes, please. I can hear you.
Okay, I'm done with my presentation.
All right. Thank you so much for that insightful presentation.
I
I'm
think
sure
we are done with
everyone
today.
has one or two. All right, so there's no question for the host. There's no question for the speaker.
Oh, okay, I think
Hello,
they don't
please
have
confirm
any
you can hear
question.
me.
Yeah, no question for now.
All right. In the absence of that, then we'll be calling it.
Okay, I think I was muted. Okay, I think this is the end of today's event. I'm sure we all learned one or two. Um, thank you guys for joining today's event, and see you guys tomorrow.